What's up, everybody? I'm Jason, and welcome back to my series looking at lights, lighting technology, and lighting for as it applies to, say, lower-end production video stuff. So I'm obviously not a Hollywood cinematographer, and I'm obviously not approaching this discussion of lights and lighting from that level. I'm interested and concerned about the quality of my lighting, but I obviously, am not spending $10,000 per light for it. So in this video, we're going to dive into some technical stuff, and I understand that's not interesting to everybody. Specifically, I want to talk about the way light reproduces color, what's called metamerism. And then I'm going to jump into directly from that the sort of technical points, or the less technical point of color rendering indices and what you should necessarily be looking for if you're looking at lights. Now, as always, I have time links in the description so you can skip ahead if you're not interested in the sort of scientific light and metamerism part of this discussion. You can jump right on to where I talk about color indices so you know what you're potentially looking for. That said, before I dive into any of this, I'm going to try and ask and answer the question of, should you need to care? Do I need to care about this stuff? Now, obviously, I was interested in this stuff, interested enough to do a bunch of research to try and understand it. And I think there is a certain amount of value in understanding this stuff just on the grounds that you can run into problems in certain situations. And if you have in the back of your head what might be going on, you might have a better handle on where the problem or why that problem's happening or how to solve that problem or how to avoid it in the first place. So I feel that while you certainly can do a lot in video, photography, whatever, without being super well versed in the physical processes that everything underlies on, I think having a little bit of understanding about what's going on is kind of useful. So in general, I would say if you're that kind of person that likes to kind of understand what's going on, then you probably are going to want to watch through the first half of this video instead of skipping to the end or just turning it off. That said, if you're not that kind of person, if you just want to know where to put a light to make the light look good, then you probably don't care. And you probably don't need to know this. And if the target of your video production or the extent of your video production is doing content for YouTube and you have no interest in growing to super commercial levels or something like that, or you're doing just travel work, you're outside, you're naturally lit, you don't have artificial lighting, then no, you probably don't need to understand any of this stuff either. If you're considering doing dramatic work, whether it's professionally that you want to grow into or you just want to do amateur dramatic cinematography and put videos together for YouTube, and your dramatic work involves potentially costumes or props, then I'm going to say maybe you want to know this. It's not something that you need to worry about tremendously, but on the same token, it's kind of useful to have in the back of your mind that this is what's going on, or this is what can happen, and I need to somewhat be aware of what's going of the situation. If your long-term goal or your goal is to get into doing commercial and especially advertorial work, so advertisements, where color rendering is incredibly important, because if your widget does not render the color that the manufacturer or the advertiser expects it to render, that's bad. Then you absolutely should understand what's going on and what the situations are. And the last consideration is if you're working with mixed lights, because this is something that's a property that changes from light to light, not just light source type to light source type. So 2 different LED lights from 2 different brands can have completely different spectral output properties, or not necessarily completely different, but different enough output properties that they can mess up, cause color shifts. So with that said, let's dive right into the technical side of this. So first thing I want to talk about is metamerism. And metamerism is defined as a color change seen in an item because different spectral emissions from a light source cause it to shift color. So we're all sort of probably familiar with color temperature, right? And we're all kind of familiar with the idea that, if you shoot the wrong color temperature for the scene, everything looks funny. So if I was shooting this, I've got a daylight light that's lighting me. If I was shooting this with a tungsten balanced color temperature in my camera, I would look super blue, and everything around me would look super blue. And likewise, if I had a tungsten light and I was shooting this with a daylight color temperature, I would look super orange, and everything around me would look super orange. So we're used to this idea that, at least we should be, that colors can change, how they appear can change based on the idea of how the camera is attempting to balance colors. And our eye and brain does this too, because the colors are shifting. If you have a white piece of paper under tungsten light, it is not the same white as if it was under daylight. Our brain is just really inherently good at, well, okay, but I'm a brain. I can make that white look white instead of looking orange. Our cameras, not so smart. We have to set the color balance manually. So the way all of this works, the reason all of this works is white light isn't a color. It's a combination of all the colors that essentially of the rainbow. And the difference between tungsten and daylight changes the relative powers of different amounts, or the colors in that spectrum. So daylight light sources, or daylight produces a bluer light. There's a higher proportion of blue, or of energy in the blue side of the color spectrum than there is in the red side of the color spectrum. Likewise, tungsten produces a more orange, amber light. There's a higher proportion of red in the energy emitted by that light, the color spectrum. There's a higher proportion of energy in the red side of the color spectrum emitted by that light than the blue side of the color spectrum. Likewise, the way color is created by things in the real world. So I have a blue shirt on. This shirt isn't blue because it's magic or something like that. It's blue because it's reflecting blue light, and it's absorbing red light and yellow light and green light, but it doesn't do this in one specific, at least for most things in the real world, it doesn't happen at one specific wavelength. So this blue isn't a specific, say 480 nanometer wavelength blue. It's a combination. There's a bell curve, there's a reflective curve, it's a combination of more bluer blues, less bluer blues, and combined together, it produces the shade of blue that my shirt actually is. So what does this have to do with colors and lights and stuff like that? Well, what happens is depending on how much energy is available in the light and the emission spectrum of the light that's being used. So if the light produces a lot more, let's just say we're talking daylight. So that's the situation that I'm sitting here in. I have a daylight balanced LED. If this LED produces a lot more of one specific wavelength of blue light and not enough of another specific wavelength of blue light, and both of those blue lights are needed by this shirt to produce the color blue that the shirt is supposed to be, the shirt won't be the right color. It will shift. And this shift is called a metameric failure. Basically, it means that the light that you were under isn't causing the color to reproduce in the way that the color should reproduce for that color temperature of light. So honestly, and actually, if you ever are interested in looking into the spectral output of lights, a great resource is to look at the people that are doing indoor and hydroponic growing. Most of them have transitioned to using LEDs and plants. So as people, we're not tremendously sensitive to specific ranges of light. Our vision covers most of the visible spectrum. There's color deficiencies and stuff like that. But if you're talking about plants are incredibly sensitive to specific areas in the color spectrum. That is what caused them to be able to do photosynthesis. So if you're growing a plant, not that this has anything to do with videography, but if you're growing a plant and you want to optimize the power that you're putting out using your lights, you want to have lights that put out light specifically in the wavelengths where the plant grows, and not necessarily, or not waste energy in wavelengths that the plant doesn't need. So the indoor growing people have done a lot of research, and you can find a lot of information about emission spectrums for at least grow lights, but LEDs and fluorescence and various technologies in general actually as well, from those sources. Interestingly, when you get into the photographic and video world, the potentially, because it's in some ways not as important to most people, or not important at all to most people, there isn't as nearly as much detailed spectral power information as you would potentially expect there to be, given the potentials for color shifts. So anyway, getting back to metameric failures and the whole color rendition problem. So one of the biggest problems with metameric failures is that you can't fix them in post. So if you're shooting and the color balance is off, you can make it a general adjustment in post to fix a color balance problem. And it's a global error for your scene. Metameric failures happen specifically and to specific materials, and they're not easily or readily predictable. So, and this is the reason that it's relevant if you're talking about, say, dramatic work with costumes. If you have a costume, say, I don't know, space armor or something like that, where you have soft fabric and hard materials that are maybe painted and other hard materials that are maybe dyed, that are supposed to all be the same color. That's the idea of the costume. Because of the way each of those materials, the fabric, the paint, and the dye, reproduce or produce their color, their spectral responses, so the frequencies of light they reflect to make that color, as well as the spectral frequency power emission, or the spectral power emissions the spectral power emissions of your light source. The interaction of that can cause one part of the costume to reproduce differently than another. And that's why I said this is relevant if you're potentially working with props or costumes where a consistent reproduction of color is necessary across the costume. And again, this is going to be something that's going to be affected primarily with artificial lights, because the color spectrums are not uniform. They're not consistent. They can be incredibly spiky. And even for sources like a warm white LED, you'd think, even though that there 2 or 3 sources are advertised with having the exact same color temperature, just say 3000 Kelvin, the emission spectrum for those sources may not be the same. And different manufacturers, they use different materials, they use different formulations for the phosphors, they use all kinds of things. You can have differences in the color spectra or the spectral power emissions for 2 lights out of the same color temperature that result in different metameric behavior different behavior of materials under those lights. So you can't just fix this in post. It doesn't happen globally. Well, I guess technically there's places where you could fix it in post, but it's not something that you'd have to track an individual thing in the frame, to apply the color correction to it, and it would be incredibly complicated and difficult to do. Likewise, you can't just fix this with a global color correction. So I'll put up some examples of some testing I did back in the early 2000s that show color shifts in materials where, for example, this Maxwell House coffee tin, the blue stays pretty consistent in color from light source to light source, but this orange slash red dot changes. And it's noticeable. I mean, obviously, it's most noticeable if you have the two pictures side by side, but it's noticeable. It's a noticeable change. It's not a tiny little error. If you were, say, calibrating a monitor talking about delta E, it's not a like 0.5. It's a significant and noticeable change. So that's the technical side. That's metameric failures and what's the process that's going on underlying. So in response to this situation, various organizations have started producing color rendering indices, for lack of a better word. The best known one is the Color Rendering Index, CRI. However, there is a number of other of these metrics that describe how well color is reproduced. Now, CRI, as far as I understand it, and I'm going to start with CRI, and I'm going to work through the four metrics that you'll probably see and what they are and how relevant they are, how good they are. So CRI was the first, and it's arguably the broadest or most common color rendering metric for sort of trying to describe how good a color or a light source reproduces colors compared to natural light, so daylight or tungsten. And it's actually older than I bet most people would think. It was originally developed in 1965, and it uses human vision as a reference. So when you get into talking about color, things actually get pretty complicated in that how color is perceived, how color is measured varies. Our eyes in human vision, we have three kinds of color receptors that are generally specific to certain wavelengths, but they cover a fairly broad range of wavelengths. And then our brain interprets that, the output of those cells in our eyes, it interprets that into the color that it perceives the thing as being. Obviously, cameras use different color filters. The materials that are used in the color filters on an RGB sensor or Bayer sensor, they're not the same materials as our eyes have. So the response to color is different. So cameras perceive color slightly different or different than we do. Different people also will perceive color slightly differently, but that's more of a variation in the theme and not so much a completely different situation, unless those persons or people are tetrachromats, which means they have different color receptors, not trichromats, which have 3 color receptors. But anyway, so because it uses human vision, because CRI uses human vision as the reference for what color reproduction should be or how colors should be reproduced, it does not necessarily correspond to how a camera will interpret color reproduction. Because again, our eyes, cameras, they're not the same things. Now, I'm going to talk a little bit about the measurement method in CRI, because the unfortunate thing is CRI is also, because it's the most common, it's the most widely used, most sort of understood or seen metric. It's also the metric that has sort of the most manufacturers have figured out how to game the most. So the way CRI testing is done is there's color swatches, and they are specifically designed artificial color samples. They're Munsell test targets. They're illuminated by the light that's being tested, and the response or the color that the light or that they reflect is measured, and that is correlated to what the color should actually be under, I want to say it's daylight is the reference that is used, but I could be incorrect on that, and I don't see it in my notes. Anyway, of the 9 or the 14 swatches, there are 8 swatches or color samples that are required. They're general swatches, and there are 6 color samples that are extra. Now, the range for CRI measurements is 0 to 100, or well, it's 100 is the top. There is no bottom limit to what a CRI value is. So a color, if you have a color, if a color swatch is green and it appears, well, let's say if a color swatch is red and it appears blue under your light source, that's not a 0. That can actually be a negative number. So 100, on the other hand, is perfect reproduction of the color. The color appears the same using the human eye metric reference standard. Now, they're not measured by people looking at color. CRI isn't measured by people looking at color. It's measured with photometric equipment, but it's adjusted based on this idea that the human eye is the observer. So typically, and this is how CRI gets gamed, typically, when you see something published, you will see a lamp or something will say CRI of 90. And typically what that, well, not typically, what that means is that the RA, or the average, of the first 8 of those 14 color swatches is 90. Now, averages are averages. So you could have 2 or 3 of those colors, individual swatches that have an average, or that have a CRI value above 90, so like say 95, and then you could have one that has like 70. And as long as everything averages out to 90, that's important, or that's good enough, I should say, for as far as CRI is concerned with measurements. Now, some manufacturers, especially in the photo light world, will publish the individual CRI values for that they measured for their lights for all 14 samples. And one of those, R9, which is a saturated red color, is especially important when you're talking about LEDs and when you're talking about the reproduction of skin tone colors. Skin tones are influenced by red because of blood in our blood vessels just under our skin. And red is also one of the biggest weaknesses in LED light sources. They don't produce red in the same volume or same intensity as a tungsten or daylight source would. They have a cutoff response there, or not as good of a response there. And so that's one of the ways that manufacturers, I've seen it from photo equipment manufacturers, but it's one of the ways manufacturers can kind of game CRI values or what they're publishing. So it's not wrong, they're not lying. It's just that they either aren't testing the more difficult 6 final specialized swatches, which isn't a requirement as far as I understand, in the average or for the average, or because they're only publishing the average of the 8 general swatches, there can be some that perform poorer than what that light suggests that what the CRI number, the published CRI number suggests that the light should, where others may perform a little bit better. So there are a number of deficiencies in CRI testing. The first thing is that because the test swatches are just artificially generated, produced, manufactured, they're not necessarily reflective of the kind of things that you're going to run into in the real world. They're specifically there's colors that are specifically designed to be manufacturable in a repeatable way that are supposed to be representative of things, but as I talked with Metameric failures, different materials, different paints, different substances, different ways that colors get to a color can respond differently under different light sources because of the interaction of their spectral response curve and the spectral power curve of the light that's illuminating them. Of course, the other deficiency is that you're not required, as far as I've ever seen, companies that report RA are not required to, or CRI are not required to report anything other than the average. So they can hide, very literally, deficiencies in color rendering because of a poorly performing value, for example, such as the saturated red R9, just by not reporting it. And you will never know unless you have a spectrometer or a proper color meter that can do spectrometry, where you can measure the CRI values and see what the light is actually producing. And of course, as I said, the RA value only includes the first 8 swatches. It doesn't necessarily, or doesn't include the specialized second 6. So that important, at least for us as videographers, R9 value just isn't there. So in response to the deficiencies of CRI, the TLCI was derived by, developed by, I want to say it was the International Telecommunications Union, or ITU. And TLCI stands for or maybe it was the BBC. Anyway, TLCI stands for Television Lighting Consistency Index. And it's similar to CRI in value and process and so forth. However, instead of using a human observer as the reference point, it uses the color response of typical broadcast cameras as the reference point. So at least TLCI is moving the goalposts, if you will, from what does it look like to a person to what does it look like to the actual cameras that we're probably using, or something that's much closer to the cameras that we're using. So in general, if your lights have TLCI values published, they're going to be a better indicator, a slightly better indicator at least, of the quality of light color-wise that those lights produce as your cameras will see it compared to CRI. Moving along, the next technology, the next color rendition metric that you may see, it's a fairly new one. It's not necessarily photographic related. It's been being pushed for better understanding or better qualification of all kinds of lights. It's called TM30. And again, it uses a process that's similar to CRI or TLCI. You have swatches that are measured, that are exposed under the light in question or test and measured. However, it steps the sophistication of the system up significantly. So instead of using only 14 color swatches, it uses 99 color swatches. Quite more relevant to us as photographers potentially is that instead of sort of ignoring skin tones, which CRI and TLCI kind of do, they don't specifically have a skin tone quality index in them. TM30 does. And TM30 requires more, additionally, TM30 requires a more complex publication of information. So it's not just, this light has a TM30 of 30 or something like that, or 90 or whatever. There's a series of charts and graphs that show how the light reproduces color and where the light's deficiencies are. So it gives people who are taking lights or using it for their light judge, for judging the quality of the color of light, it gives them a better understanding of what the light actually does and where it is and isn't deficient. Now, unfortunately, TM30 is not widely used. It's available, for example, if you have a Sakana color meter, you can get TM30 measurements from that, as well as CRI, TLCI, and finally, you can get SSI, or light measurements on that kind of light meter, which brings me to the last metric that I want to talk about in terms of color fidelity of a light source, and that's SSI, or the Spectral Similarity Index. So where all the measurements that I talked about previously, CRI, TLCI, and TM30, they all look to assess the quality of the light by looking at what a theoretical observer would see if they looked at a color under that light. So it's kind of a roundabout way in some respects of looking at light quality, because you're going, okay, well, this swatch is supposed to be this specific color blue. Under this light, the error is so much in this direction, therefore it's something. And again, even though it's being measured by electronic instrumentation, it's not somebody just looking at it. There's a projection happening, a mathematical transform happening to understand or project how that light would appear to an observer, either a human in the case of CRI or TM30, or a camera, a broadcast camera in the case of TLCI. So when all these new lighting technologies came out, fluorescence, LEDs, even there were some people that were even testing plasma lights, like plasma TVs used, but as a light source. Hollywood, and you know it would have to be Hollywood because they have way too much money spent in production, of video and whatnot, movies. The budgets are huge, the costs are enormous, and the quality standards are through the roof. Hollywood looked at the problem and said, how do we figure this out? And the Academy of Motion Pictures, Arts and Sciences, the people who do the Oscars, put together a special interest group or a working group to look at how do you figure out how effective or close or whatever a light source is. And they went a completely different direction from what all the other metrics were doing by looking at samples under or SWOT colors under the light, etc. They straight up said, you measure the spectral output of the light and you compare it to the light that you're comparing it to. And it's a great way to do things, honestly. So the problem, as I said, with swatches is that you're measuring something indirectly. You're measuring the color quality of the light indirectly. Now, you can make an argument that's fine, because if two swatches appear, or a swatch appears the same color under two light sources with the right observer, so say a broadcast camera, it's going to appear the same color in the recording of the broadcast camera. Okay, but it may not appear the same color to the people who are painting it or dealing with it. So if they're matching colors with their eyes, they're going to match colors potentially differently. Then the thing goes out onto the stage, the sound stage, onto set. The cameras are looking at it, and the colors are not the same all of a sudden. Or likewise, what happens when the cameras change? So there is no guarantee that the color filters in every generation of camera are going to be the same. And as we've seen from the evolution of color science in, for example, Sony's mirrorless cameras, they are changing because Sony mirrorless cameras keep having, I won't say keep having, but Sony keeps improving and altering and addressing and adjusting the color science that's going on in their cameras. And part of that is is changing the specific responses of color filters on the sensor. Part of it also is math that's going on in processing that. So with something like TLCI, you can have two swatches that appear the same by the standard, but then the camera changes and then they shift, or they don't appear, they're no longer the same. So the approach that the Academy of Motion Pictures, Arts and Sciences took, Hollywood for that, for lack of a shorter word, the approach that the Academy took is to compare the actual spectral power outputs of the light sources. So it doesn't matter what technology goes into a light source if the spectral power output, so the amount of energy that's produced at each frequency through the visible range, is the same as the output of another light source, they're both going to render color identically. And it doesn't matter if one's fluorescent and one's LED and one's tungsten and one's HMI. If the spectral power curve is identical, the light sources, the light that the light sources produce is identical. And you don't have, it doesn't matter if the camera changes. It doesn't matter if you're painting something as a person looking at it and making adjustments to color and then having the camera look at it. They're going to be the same. So in some ways, the Academy's Spectral Similarity Index is it's much better potential in some ways at guaranteeing color matching or color accuracy or reproduction of color. So matched reproduction of color of light sources. Now, of course, the problem is that nothing has perfectly identical spectral outputs. That's sort of just the reality. So the SSI measurement scale is 0 to 100, basically sort of percentages or whatever. That 100 is a perfect match. The two sources have identical outputs. They don't have to be the same process. Like one could be tungsten and one could be LED, but the power emission or the spectral power that those two light sources are identical. The Academy gives some more information on SSI, some ranges. So 90 or better is going to have a very good reproduction. 80 or better is what they consider pretty good color or color reproduction. If you can be in that range, you're going to have no real issues. If you have 60, if your two sources have an SSI of 60 or worse, then you can expect that you're going to have color rendering issues. Now, unfortunately, the downside of SSI is, as much as it sounds like it would be the great solution for us as videographers to, now we know for sure that our lights match, almost nobody publishes SSI data or tests with SSI data for their lights. Of course, it is comparing two sources, so it's also slightly probably more useful in the field, but one of those sources that's comparing could be tungsten or daylight. So if you have a daylight balanced LED at say 5500 Kelvin, you can compare that to the black body emission range of daylight light at 5500 Kelvin. And, have a similarity index, we'll call it, for that. So nobody really uses it. And unfortunately, if you want to measure it yourself, the easiest way I've seen to do that is to use a color meter, and those are about $1,500 a pop, which puts you, at least the good ones, which puts it pretty out of the range of something that you're going to be just, doing if you're a YouTuber or even a small budget production, videographer. That gets you well into the range of cinematography type, serious production work. And you'll find that cinematographers that are working in advertising and Hollywood type productions and even potentially serious TV document or TV series work, they will have color meters and light meters available, in their kit so that they can measure this stuff and ensure that they're getting the right color balances, the right reproduction ratios, and whatnot. So to wrap this up and summarize it, basically, the important thing to understand is that not all light sources produce the same spectral power curve. I say natural, but tungsten daylight, those light sources, black body light sources, produce a power curve that's continuous, as I said in my previous videos talking about them, and you can generally make adjustments from one to the other is a global adjustment because of the continuous nature and the way that the way that light is curved, or the way that a light emits color or power as at colors. However, for artificial sources, the spectral emission curves can almost always have, and by artificial sources, I'm talking fluorescence, LEDs, HMI, plasma, anything other than tungsten or the sun, that they will have spikes and valleys. They can have places where they produce no color at all. They can have places where they produce way more color than they should, and it's just okay. It's assumed to be okay because, for example, the human eye isn't tremendously sensitive there, so you don't see a color shift. or a huge color error from that. These light sources interact with the dyes and pigments and the materials, the paints, materials, products, etc., that you're producing or using to produce the light or of that subject, of that material. And depending on how this source, the power spectral or the spectral power emissions or the spectral emission curve for that source is, can cause specific colors to shift. The unfortunate thing is that this shift is not global. It's specific to a material under under those lights. And so there's no easy, or I want to go almost so far as to say fix for this at all in post. There's really nothing that you can do to fix the response, because it's not a global change. The best case scenario would be it's something that you could track, but then it would get really complicated, difficult, and expensive to deal with. So, as I said, does this matter? We open this off and with this question, and the response to that I have is generally no, it doesn't. It's, I think, important to understand. It certainly matters if you're getting, or if you intend to, or you're like want to work towards a Hollywood level of production. But if your focus is just YouTubing, it's not something that you need to it's not something you need to worry about. It's nice to know, but it's not something you need to worry about or try to address potentially, because quite honestly, most people are never going to see a problem. It's not going to be something that you're going to lose money over or be sued over because you reproduced some color of some product wrong. Even if you're a YouTube reviewer and you get the color of a product wrong, you're probably not, you're like in a review, you're not going to get sued for doing that or for having that. It's not the same kind of problem if you were actually working for the advertising campaign for that product and got the color wrong. So with all that said, I'm going to just sum this up with, as always, you want to aim for the best quality light that you can get. So the highest CRI, TLCI, whatever that fits in your budget. If your budget, and I started this whole YouTube video lighting thing out using high CRI, screw-in home LED kind of lamps as my light sources. They were like $10 or $15 a pop, screwed into the cheapest lamp socket that I could put them in and stuck in the cheapest softbox that I could get. If that's your budget, get the best lights the highest CRI lights that you can get. Broadly speaking, that will be good enough. Like, so don't buy the cheapest lights. Don't spend $6 on cheap lights if $10 get you 90 plus CRI lights. You'll have the peace of mind of having better color reproduction. So that wraps up this fairly long, fairly technical video on color rendering, metameric indexes, and color rendering metrics. I hope this was at least a little bit informative. I know it's pretty technical, and that's always a challenge to digest in video. If you did find this useful or informative, please consider smashing that like button. Also, please consider subscribing. As always, thanks for watching, and I'll see you next time.